Okay, BC Formula Pretest. You guys also need to do the AB one because you are half your test is AB. So this is specifically BC formulas. Um, so parametrics. If x equals g and y equals yt, then dy dx equals dy dt over dx dt, which is going to be f prime t over g prime t. So that's what we're going for there. Number two, if x equals g and y equals f, then the distance traveled by the particle from A to B is what? Okay, so distance is the integral of speed, which is the integral of the absolute value, the integral of the square root of dx dt squared plus dy dt squared dt. So for us, we're going to go from A to B, square root of g prime t squared plus f prime t squared dt. So that's what we're going for there. If x equals g and y equals f, then the acceleration vector is vector. So the acceleration vector at time t is the second derivative of position with respect to time, comma, the second derivative of y with respect to time. So that's going to be g double prime of t, comma, f double prime of t. They usually like to use these little sharp bracket things, but I think you probably put parentheses on the AP test. Okay, find an integral expression for the area. Okay, so you need to remember that the area of a polar curve is 1/2 r squared d theta, and so we're going to go and it slices it up like that into these kind of sector-looking slices. So it's going to be 1/2 alpha to beta, and then let's see, the radius is equal to f theta, so we're going to put f theta in there, some function theta squared d theta. So that's what we're looking for there. If r equals f theta, then dy dx equals what? So that's going to be dy d theta over dx d theta. And we have to remember that in polar, x equals r cosine theta and y equals r sine theta. If you don't remember how this works, this is theta. This is your xy coordinates in Cartesian. This is r. So if you want to know, this is the x coordinate. If you want to know x or y, you got to use basic tricks. So if you want to get x from r and theta, you got to do, well, adjacent over hypotenuse. So it'd be cosine theta equals adjacent over hypotenuse, and that's how you get that. If you want the opposite side, you need to do sine theta equals opposite over hypotenuse, and that's how you get that formula. I mean, you should probably have them memorized, but they're easy to figure out. So in this case right here, this is going to be f theta cosine theta, and this is going to be f theta sine theta. So then dy d theta is going to equal, don't memorize this, please don't memorize it, just figure it out. It's just product rule. It's easy. F prime of theta times cosine theta plus f prime theta times sine theta, right? It's product rule. Dx d theta is going to be f prime theta sine theta, but negative, because derivative of cosine is negative sine, plus f prime theta cosine theta. So that means that dy dx is going to be f theta cosine theta plus f prime theta sine theta over negative f theta sine theta plus f prime theta cosine theta. Now, do not ever use this as a formula. Just whatever the r is, just take the derivative of it. But this is just a very kind of generic way of showing the work to get those. Number 6, find all the values of theta for which r is at the pole. So at the pole means that the radius equals 0, which is like the origin. And so if you want to figure out when a curve is going through the origin, the pole, you set the radius equal to 0 and you solve. There's often trig involved in these. Alpha equals, when does sine equal 1/2? That first angle, pi over 6. So let's see. So that's the reference angle, and then we're quadrants 1 and quadrants 2. So theta equals pi over 6 plus 2 pi k. And theta equals, quadrant 2 would be 5 pi over 6 plus 2 pi k, right? Pi minus alpha. And so we're just looking for the answers between 0 and 2 pi. So it's just going to be these two on this problem. Those are the angles that the curve is going through the bowl. Sketch a curve. Can you sketch a polar curve? Now you can try and remember what these shapes are. If there's no plus number, then that's like a circle or a rose curve. If there's a 1 inside, that's a circle, which is really a one-petaled rose curve. If there's a plus out here, then that's like a cardioid of some type. Limason, I guess, is what they call that whole family. Cardioids are one type. Now, if these are equal, then that's a cardioid. So they're kind of the heart-shaped lung thing. If they're not the same, then it's either got an inner loop or it's convex or flattened kind of. So I usually just plug some values in anyways. It's good to just have a rough idea. Now, cosine, if it's cosine, that's horizontally oriented. And if that's sine, it's vertically oriented for any shape. And again, if you don't remember that, I might just plug in some values like 0, pi over 2, pi, 3 pi over 2, 2 pi, easy values. I might plug some more in to figure out what's going on if that's not clear enough. So plug 0, cosine 0 is 1, so that's going to be -1. Cosine pi over 2 is 0, so that's going to be 1. Cosine pi is -1, so that's going to be 3. Cosine 3 pi over 2 is 0, so that's going to be 1. Cosine 2 pi is 1, so that's going to be -1. So these are the angles and those are the radius. So we're gonna get radius as big as 3. So, and we're graphing these on a XY coordinate plane. So 0, -1 means we're facing to the right, but then we're to the left because it's negative. Pi over 2 is up here. Pi is facing to the left. And 3 pi over 2 is down here. We're facing down and we go down 1 unit, and then 2 pi over back here. So it's like we start over here and then we end up over here. And so I think this is the one with like the inner loop like this. And that's the direction. It starts here and it goes this way. It's really good to know the direction. You could confirm that it goes through the pole there by setting the r equal to 0, which might be good. You might need those anyways. So let's see if we can do that real quick. Set it to 0. It's usually some pretty basic trig. It's going to be 1/2. Alpha equals pi over 3. Quadrants 1 and 4. Theta equals pi over 3 plus 2 pi k. And theta equals 5 pi over 3 plus 2 pi k. So it's supposed to go through pi over 3. So that would be like right here. We get a 0. So from here, between here and this point, it goes through the origin. So that makes sense. And then 5 pi over 3 would be over here. We get 0. So after it gets to here and before it gets to here, it goes through the pole again. So that does confirm that. So we call this a limason with an inner loop. Not that you need to remember the names, but it's just good to recognize them. Usually, you're probably not going to have to graph any of them on that AP test. Well, on first response, you might need to. Multiple choice. Usually, they'll give you a picture, and it's just good to know what you're looking at. Okay. In the back, we got a little logistic Euler's method stuff here. So logistic, you should know that the differential equation for logistic has the exponential part of it, and then it has a limiting part. So as the population gets close to carrying capacity, this gets close to zero and it causes the growth to go to zero. So the graph looks like that. And then the inflection point is at half the carrying capacity. And that's the point of greatest growth, those two horizontal tangents. Okay, so, looking at this, you got to first, make sure it has the form that you want it to. This needs to be a single p, okay? Otherwise, you might misinterpret the values here. So I think we're going to need to factor a 1/30th out, which is fine. So if we factor 1/30th out, that's the same as multiplying, right? Dividing by 1/30th is the same as multiplying by 30. So we divide 1/30 out, get a 60 here, minus p. So that's your carrying capacity. This is your k value. And then the limit as t goes to infinity of logistic growth is always going to be the carrying capacity. So that's going to be 60, right? The k value is 2/3 if you need that. Okay, this one here, this is actually the logistic growth model. So we derived it. It was kind of a pain to derive. So I'd memorize it. M over 1 plus A e to the negative m kt. And so there's got to be a 1 here. So we're going to divide a 2 out of everything on the top and bottom. Right? And so this is your carrying capacity. So I could answer the question that they're asking, the limit as t goes to infinity of this, which you could probably answer that anyways without having done this, because this is going to go to 1 over e to the 2t is going to go to infinity. That's going to go to 0. It's going to be 30 over 2, which is 15. So that makes sense too. Finding the k value is a little more work because you got to set -2 equal to negative mkt. You got to find the m value first, which is 15. The t is, don't need the t, so k equals 2/15. And the a value takes a little more. We know the a value there. So okay, so that's logistic growth, which is good to know the facts about it. Be able to recognize it. Euler's method. I wouldn't memorize this table. I would be able to create it if you need to. On free response, I probably wouldn't use it. But it's using a tangent line. So this is just the way we usually find the equation of any line. And so we have some old y and x pair, known x, y pair, and then we're going to find the derivative at that point and create a tangent line at that point, and then use it to find the new y at a certain new x. Now, so if we solve this, y new equals y old plus y prime old, and then x new minus x old is delta x. It's usually consistent. So here, there's a table already kind of filled out. You could figure out that the delta x is 0.5, and it could be negative sometimes, by the way, too. Actually, yeah, delta x is 0.5. And so this is the y value right here, right? And so the new y value equals the old y value plus the derivative times delta x, which is going to be 1.5. So that's going to be 5.5. That makes sense. So this one is going to equal the previous one plus f prime of x times f prime. So that's going to be 8.5. Anyways, so 8.5. You have the formula for the length of a Cartesian curve. So this is a curve from like last year in AB that we've been dealing with this year too, but the length of it, we didn't cover that in AB. The length, it's very similar to the length of these other polar curves and parametric curves, it involves a square root. But it's going to be dx. It's going to be a to b. It's going to involve the derivative squared, but this one has just a 1 in it. Now, this is derived, if you want a quick reminder, this is derived if you have a curve and you want to find the distance along the curve. What we do is we estimate it with a secant line. But if we do a bunch of them, really tiny, infinitely many of them, then we're going to get, it'll approach the exact length. So we're really doing the hypotenuse of this little right triangle. So it's going to be delta x squared plus delta y squared. And so it's really just it's Pythagorean theorem. Now what we could do is we could divide a delta x squared out of each of the terms inside, and that's the same as division, right? And so then the square root of delta x squared, well, delta x is like dx, so we get a dx on the outside, and then delta y over delta x, that's the derivative of y with respect to x, right? So that's a derivation of it real quick. Now, the other length formulas, why don't we just mention them right now? For polar, the length is the integral of some angle to some angle. That's why we usually alpha and beta. It's a and b. I usually use Greek letters for angles. Square root, and it's going to be r squared plus dr d theta squared. So it involves the derivative again, and the independent variable is theta there, so it's going to be with respect to theta, but it involves an r squared here. Now, we did a bunch of work to derive this. It comes from the same idea here, but it's really messy. It involves a bunch of trig until we clean it up and get to that. So I think it's just worth memorizing this one. For parametrics, it's from some time a to some time b. The independent variable is time, and it involves there's two derivatives. There's dx dt squared and dy dt squared. So they all involve square root. They all involve the derivative squared. Some of them just have like a 1, or this one just has a 1. This one has r squared. So they have a lot of similarities, and I'd use that to help remember them. But then you got to remember the differences. A geometric series with the first term k and a ratio between terms of absolute value of r less than 1 converges to what? Converges to the sum of the series, k over 1 minus r. Now, we said the first term was k, so we put a k there instead of an a. And it does converge because the absolute value of the common ratio is less than 1. 12, the coefficient of x minus a to the fifth power of a Taylor series with y equals fx centered at x equals a is what? It's the fifth derivative value at the center, right? X minus a to the fifth power over 5 factorial. That's how we find each term in a Taylor series. This is the coefficient, just that. But you need the 5 factorial. That's part of the coefficient. Do not include the x minus a to the fifth power. That's not part of the coefficient. 13, find the interval of convergence. So we'll be doing this a lot. We're going to use ratio tests. We're going to take the limit as n goes to infinity of the absolute value of 5 minus 2x to the n plus 1 over n plus 1 divided by the nth term, or multiplied by its reciprocal. Okay, then we're going to clean this up. So it's going to be limit as n goes to infinity of n over n plus 1 times 5 minus 2x. Now, this is going to go to 1, so this is going to go to the absolute value of 5 minus 2x, and then we need to show that it's less than 1. And then we got to solve that absolute value inequality. Now, you could do that. You can solve this however you want. You can say, all right, well, this is between 1 and negative 1, and solve it. Or you could try and get this coefficient to be a 1. Divide everything by 2, so you get 5 halves minus x. Absolute value is less than 1 half. And then this is the center of your interval of convergence, and the radius is 1/2. So this is kind of interesting. It gives you the radius. So it gives you 6 halves, which is 3, 4 halves, which is 2. So for sure converges in between those. That's the open interval. But then we got to figure out, we got to test the endpoints, right? And so we got to test x equals 2, and we rewrite the power series as a number series. So we plug a 2 in for x, and we get 1 to the n over n, which is just n equals 1 to infinity of 1 over n, which is the harmonic series. So it diverges. Or you could do p series, p equals 1 diverges. On free response, you better show that work. You better name it. You better show the work for the test or whatever. We're going to do the other endpoint. X equals 3. Rewrite the power series, n equals 1 to infinity. If you plug 3 in there, it's going to be negative 1 to the n over n, which is the alternating harmonic series. Okay. Now, some of you guys on some tests recently you've just said, you said, oh, it's alternating harmonic, even though it's not alternating harmonic. Alternating isn't alternating harmonic. 1 over n is a harmonic. With an alternating makes it alternating harmonic. If it's not just a single n to the first power on the bottom, p series p equals 1, it's not called a harmonic. You could use the alternating series test on any alternating series, right? But this one does converge. So 3 works, 2 doesn't. Your interval of convergence is this or this. Okay, you got to test the endpoints up. 14, list the 4 non-zero terms of the Maclaurin series. So this is just testing. If you remember the Maclaurin series for E, it's 1 plus x squared over 2 factorial plus x cubed over 3 factorial and on, right? And this is actually the first over 1 factorial. This is x to the 0 over 0 factorial. So it's this pattern. You don't need to memorize separate terms. It's one big pattern. So the answer is going to be 1 plus x squared over 2 plus x cubed over 6 for that one. First 4 non-zero terms. Now this one's more complicated. I would write down what sign is. Sign is e to the x, but just the odd terms, right? So this is to the 0. That's even. So it's x, and then it's alternating minus x cubed over 6 plus x to the 5th over 5 factorial minus, right, x to the 7th over 7 factorial. Then we're going to plug x squareds in for all the x's. So it's going to be x squared in parentheses minus x squared cubed over 3 factorial plus x squared to the 5th over 5 factorial minus x squared to the 7th over 7 factorial. And then we're going to multiply everything by a x cubed, and you're going to distribute it to everything. So it's going to be x to the 5th, rules of exponents, minus, this is x to the 6th, x to the 9th over 6, plus, this is x to the 10th already, x to the 13th over 24, 120, minus, this is x to the 14th, x to the 17th over, this would be, what is 720 times 7. You could probably just leave the factorials. 14, carry the 1, 49 is 50. So it'd be 50, 40. So got to be good at building Maclaurin series from other Maclaurin series. Write a formula for the Lagrange error bound. Okay, so Lagrange error bound is, and I would always write this down whenever I have to use it. Now, by the way, I'll write that down in a second. Lagrange error bound is the n plus 1th derivative at a c value, x minus the center to the n plus 1 power over n plus 1 factorial. You need those parentheses, where c is between the center and the value we're evaluating it at. So you're going to be given all this information. And where f to the n plus 1 of c is a maximum value, okay, because this is worst case scenario. Now, in general, on the AP test, error is represented with say like f to the 2. So that would be the exact value of plugging 2 into the infinite series, but then we're going to minus like the Taylor polynomial third power with a 2 plugged into it. So that's the error. Error is the absolute value of the difference between the actual value and the estimate. That's exactly the error. And then what we then do is we then say, well, it's less than the Lagrange error bound, or it's less than the alternating series error bound. But these expressions will pop up. Sometimes they'll describe them with words, but this is how we write error for series. The actual value of the function minus the estimated value of the Taylor polynomial. So because it's an estimate if we don't take all the terms. If we take all the terms, it's perfect. There's no error. That's it. Hopefully you know your formulas. This didn't cover every single thing, but it covered a good variety of the different kinds of things that you should know.